set has not spam and 1% is spam, then the model will obviously show a test accuracy of attain accuracy of 99. You might think that the model is performing very well, but if you give an actual spam message or spam email, it will hardly able to detect whether it's spam or not, because the amount of the huge gap, it is so imbalanced. The data set is so imbalanced that it is not able to capture the minute thing which it's required to capture. That it is supposed to capture that minority, but it's not able to do that. So the biggest the example I'll be giving is not related to NLP, but if you think it like that way, if you are creating a model which is supposed to detect cancerous cells, and the training data set which you have fed in has mostly non-cancerous images, how come it will be able to detect a cancerous image or a cancerous CT scan? Because you have not balanced the data set. The model is not able to generalize between the cancerous or non-cancerous. So that's the same case out here also. That the balancing is very much required to avoid bias. If the 90% of the reviews are positive, the model might always predict positive. That doesn't mean the model is performing too well. It's just not able to detect the anomaly. So we have techniques like SMART to create synthetic minority samples or oversampling in the fields, and even normalization scales features so that no one dominates. It's like preparing for your batter, getting the ratio right for the balanced outcomes. You can't just mess up the ratio. The ratio is important to get the right taste out of the model. Finally, we have step 6, where we build and train the model, where we choose a task, and for a task, for the specific task, we provide the model with a algorithm. It could be naive bias or LSTM. It could be transformers, but we have to identify the task. Like if the task is simple, like a sentiment analysis, we can easily do it with naive bias or LSTM. But if it's something like translation, transformers are required. If it is something about classification, we can bring in SVM or logistic regression. Or if it is about complex documents, we need deep learning. So this is the decision we make based on the task we are given with. So and how can you conclude whether a model is fitting perfectly with the use case or the task you are given with? For that, you have to conduct some evaluation. Evaluations have to be conducted based on metrics like precision, recall, F1 score to ensure reliability of the model in the task you are given. So this overall journey, this whole journey shows that how the raw text is clean, then we structured meaning to it, then we converted it to numbers, and finally we trained the model ready for action. This is the systematic framework we have to follow if we are making any NLP use case. So is this step-by-step workflow clear to everyone? But I believe everyone has understood, or anyone else need doubt. Are you guys following up with me? I could barely see you. Any mics on.
Yes.
So we will dive into the workflow step by step.
Dave,
Yes.
sorry for interrupting you. A quick time check. We have got 5 minutes more in the session. So maybe at some point in time, wherever you feel it is appropriate, maybe we can break. I mean, at that point in time, we can extend in case if the milestone is very near. But I mean, we just have 5 minutes more to go.
Okay. The session was only for 1 hour 15 minutes.
Yeah, 90 minutes.
I think I have extended my conversation.
Yeah, no worries. I think it's important that we talk about all these topics because the implementation is one part, but how the basic algorithm, how the things are actually working beneath, that's very important. So please go ahead. Dev.
So as we have already discussed before, that the first step of NLP is about import and load. Everything about import and load. What and all tools we require, the libraries, we have to bring those things in. So majorly we are bringing in two building blocks. The first one is libraries that give us the powerful tools, and the other one is the data that fuels the model. So think of this as stocking your workshop with the right equipment before you start building. With these foundations, the rest of the process will be chaotic and inefficient. Like if you don't select the right library or you don't have the correct tool for your task, it will become a chaos for you later once. Eventually, you need those tools and libraries for the task. As you see on the slide, the objective here is straightforward, like load essential tools and data to kick off your project. So we'll begin with the overview that we are importing the libraries, example NLTK, Spacey, and we have transformers and pipeline. So I have attached the code snippet along with the slide, as you can see. Hello. Yeah. So we are importing NLTK, importing Spacey, and these are just not a random choice. They are tailored for some needs. They have some specific use case in the code. Like it has its own importance in the code. Then we load the data set. If it's a CSV file, we load it using pd.read CSV. Or if it's a plain text file, then we load it in another way. Let's discuss about the libraries like NLTK is mostly educational purpose, has some features like tokenization, POS tagging, and small data set. Okay, quick question. Can anyone tell me what is POS tagging? Just to check. Yes. Okay. Can anyone explain me what is POS tagging? No one. No one has understood anything yet.
Basically, it was used to improve grammar uh, in the thing that we are making. So it was used to improve the grammar of this.
You are partially correct, Rizwan. Um, why
No, it's
partially?
for labeling noun, verb, or
Exactly.
adjective in the sentence.
Exactly. That's the complete answer. It is used for grammar, but for labeling the tokens, what kind of grammar it is, what kind of speech it is, what part of speech it is. So if you have to remember this, like POS is part of speech tagging, means what part of speech is connects to what, like whether it's a noun or a verb. Like that's how you remember POS tagging. And what is a similar tool we had, technique we had, apart from POS tagging? Anyone remembers that? Which is used to add meaning. Apart from POS, we have also discussed one more tagging technique. Anyone remembers? Anyone?
NER tagging.
NER tagging. Perfect. We have also discussed NER tagging, which is named entity recognition. Then we have Spacey, which is a industry level library used for pre-processing. It is used basically in large data sets where we deal with large scale NLP. And Transformer itself, Hugging Face itself is a state-of-art pre-trained model, which is being already pre-trained. We just need to fine tune it over the use case we have, the top layers of it. Then we have data sources like CSV, JSON, and text, depending on the various types of files. Like if it's a review, transcript, or an article, it will be CSV. If it's a social media feed or an API crawl data, it will be JSON because JSONs are lightweighted. And then we have textual data like article, books, legal docs, and research papers. So these are different data sources we have. So the best practice I'll suggest from my end is the moment you import libraries, the moment you load data, the first thing you should conduct is inspect the data shape, the structure what you have loaded, the structure of the data set you have loaded. Then match the library to project scale and complexity. Like whatever complexity is required in your task, whatever is the scale of your project, that level of libraries are required in your field. So you have to understand what is the complexity and what is the scale of the project before you import libraries into your code. So these are the suggestions from mine. I believe the first step is clear to the audience. Everyone is pretty clear with what is the step one of NLP workflow.
Yes, sir.
Yes.
So we are already out of time. So should we compile? It will take another half an hour if we will try to complete all the steps. So what should be the calls, sir?
I think maybe what we can do, and again, I know that there are different commitments for each of the individuals, right? So maybe, and I'm assuming that we have reached a point where we can actually break in. We can start from step one in the next conversation, right, and then go on
Yes,
to the
sir.
step two, and then of course the implementation part that you want to go through, right?
Yes.
I mean, that's my suggestion. In case if you have any other point, I'm referring to the people in this forum. In case if you have a different view, please go ahead and share. Okay, so I already have an acknowledgement. Yeah.
Is it to
So,
me now?
no, I was referring to everyone. In case if
Okay.
they have a different point of view, if they're very excited about the topic and they think that okay, breaking it in between now is not good, or maybe somebody is
Yeah, sir.
thinking
This is
that
the
maybe.
abrupt place to be stop.
Okay.
Whatever
Okay.
we
So
have.
why don't you go ahead and complete the step in case if the participants are okay with that. If Rizwan, Anil, Hamza, Gusehj, maybe if you're okay with this.
Yeah, I'm okay to continue.
All right. Okay. Please go ahead.
Okay. Nice. The reason why I wanted to go ahead because whatever we have learned till now is like the building blocks of our foundation, the core concepts. And if we will stop here, then the whole purpose of this workshop will be not fulfilled. So to understand the pre-processing workflow is very important. So as we have already loaded our data and tools, let's move on to the next step, cleaning the data. So the raw data is messy and inconsistent. We have already discussed. It contains punctuation, HTML links. It has case differences, emojis, typos, markups. So we have to deal with all such kind of noise and irrelevant elements present in our raw text, which after which we can make it ready for the analysis. So in this step, we will cover all of these aspects to make the text ready for model. And one more thing we have to make sure is that the model focuses on the meaningful linguistic signals rather than just the noise. Like we have to remove noise, but we don't also need to lose the linguistic signals. We don't need, we can't afford to lose the features which is relevant to our model. So that's the understanding we'll create now that this, as you can see, there is an illustration out here that that the noisy data has been cleaned to clean text and that the lady is using it to analysis. So the purpose is quite clear here that we strip away the junk from the text and we go through these steps that make it more concrete, more useful for us. So starting with the very first technique, which is lowercasing, we convert all the text to lowercase to standardize the token. Like why to treat an apple with a capital A and an apple with a small a differently? They are the same words, but we have to we don't have to uh, fill the vocabulary with the same words, which just because of the case. First, the machine will treat an apple with a capital A and an apple with a small a differently. So we need to standardize the text by lowercasing everything. Then comes the punctuation removal. We strip out and reduce the token variation, like hello with an exclamation becomes hello. The punctuation barely adds into the uh, adds into the like the text, it barely gives any edge to us. We don't need that punctuation. So such punctuation which is not relevant to us can be removed so that the nuisance can be avoided. Then moving to the next technique, we can remove URLs and HTML tags. Yeah, we can remove URLs and HTML tags. Uh, this even has no linguistic value in itself. It's a waste of a resource for our model. Then dealing with emojis and dealing with emoji itself is a task in somewhere, because we some cases in some cases we might need to preserve the emojis, and in some cases we can simply ignore it. Like the case which we need to consider emoji is sentiment analysis. If the task given to us is a sentiment analysis, for sure we have to consider the emojis. But if it's just a simple text extraction task, we can simply avoid the emojis. So, and there is one more way that we can represent emoji, that each emoji is known by its name. Like for smiling emoji is there, it's known as smiley. Like different emojis have their different names. So you can add that name to the text rather than keeping that emoji. This is also a technique used for sentiment analysis only, to convert the emojis into their name. Then removal of extra spaces, as it has no point in the model training, carries no value. And the spellings and the contracted ones, like we have to expand the contracted terms, like can't can be written as cannot, and if there is any typo error or the spelling error, we have to fix it so that the model doesn't get trained on gibberish or rubbish data. We provide it something relevant. That is the whole purpose of cleaning the data, so that we provide, like it's like, again, it's like cooking only. Like if we are cooking, we just can't put raw vegetable into the vessels. Or like we need to wash it, we need to peel it, we need to cut it. Then we throw the part which we don't need, and we add the part which we need as a flavor. So even think it that way for NLP also. Like you keep the valuable signals and you have to tailor it on your own. You have to tailor it on your own based on the task given to you. Again and again repeating this thing, that you have to understand the task given to you, then only you can tailor the text. Then um, the okay, then we have covered all the techniques in the cleaning this. I don't think so. We have covered all the techniques in cleaning the text. We can move to the next slide. The next slide says add meaning, which is actually the linguistic enrichment. So till now we have cleaned our data. We have a well cleaned.
I'm sorry to interrupt. I
Yeah.
just had one question. Like,
Okay.
if is there any issue? Like, is there any issue that can come? Like, suppose there is a sentence in the data that Apple is an organization, and in place of Apple, the at the rate is there in place of A. So while that data cleaning, the spelling would change for Apple. So will it correct also in the second step?
So like you are telling me that Apple has an @ symbol rather than using a letter. That's what you're saying.
Yes, yes,
So
yes.
it will correct it, and for that we have to consider the context also, like whether it's used as a fruit in the sentence or whether it's used as an organization.
Yes, so if the sentence is Apple is an organization,
Yeah,
so like then it will identify it and then it will correct the spelling in the second step itself.
yeah, it will correct the spelling in second step itself, because it's an organization. It has to be identified as a NER in the next step we are discussing now. If you
Okay.
understand what I'm saying, like
Yes, sir. Yes.
if the text has to be understood using part of speech and NER, we need to divide the text into meaningful terms. Like if the apple is a fruit, then we have to term it as a fruit only. If apple is an organization sentence, then we have to term it as an organization. Or else the NER will fail. It won't be able to identify such entities from the text.
Okay. And
Did
so
I made
this
yeah.
in third step, that POS tagging, while doing this POS tagging, as we say, it's used for grammar. So basically, it will take care of the proper nouns and the common nouns also. Like proper nouns have to be in capital letters or small letters. So will it take care of these things also?
Yeah, it has to take
Okay.
care of that thing. It has to categorize between nouns and verb and adjective, so that if you would see there is a parse tree. There's a parse tree at the bottom of the slide. So that's how
Yes, yes.
it executes the part of speech. It makes a tree out of words and it connects them together, giving a more linguistic approach to the text. Like the meaning of the text could be understood more easily.
Okay.
Like whether
Okay.
the apple was a
Thank you.
fruit or an organization in the text, that could be done using this parse tree. We just can't
Okay.
look at one word and decide whether it's a fruit or no one can do that. Not even humans can do that.
Yes.
We need to read the sentence or the sentence before that, the preceding one or the succeeding one. Then only can figure it out. We even do that while reading novels and books. That if we get stuck in a word, we are not able to figure out the meaning of the word. We try to read the sentence completely. Then we somewhat we are able to figure out what could be the possible meaning of that. So this is what we are expecting in the machine also. For that, POS and NER is very helpful to do such linguistic enrichment. So
Okay,
did
sir.
I
Okay.
make myself
Thank
clear?
you.
Yeah. Okay. Okay. Then we have dependency passing. Dependency passing where we reveal what to whom by mapping grammatical links. We connect, like as you said, we connect the proper nouns with the verb which is done by it, and at what level it's done is described by the adjective. So we connect all of them together, and we create a dependency between them. We create a parse tree of out of it, which help us to tag the parts of speech. That's how the parts of speech are tagged. So is there any difficulty or doubt anyone finds in this add meaning step of our workflow? Should I move ahead? Okay, I'll take the silence as no. Okay. Going to the next step. Now that we have cleared and we have enriched the text with meaning and structure, the next challenge is how do we actually feed it into the machine learning model? Obviously, we can't feed the textual data in whatever extent we clean it. We can't simply feed into the text data. We need to convert it into something which machines can understand. We need to translate everything into numbers so that the machine can uncover patterns and make sense out of it. So this step is called, in brief, it's called vectorization or numerical representation. It's like turning human language into maths that computers can understand. Why is it essential? Because words are just symbols, but numbers allow model to spot similarities, differences, and relationship between them. So that's an extra edge we get when we convert these textual data into numerical ones. Let's start with a very basic method of feature extraction, which is bag of words. We have already discussed a bit about it. And that bag of word is one of the simplest technique, and it is responsible for counting how often each word appeared in a document. Like if I say same generic example, if I say I love dogs and I love cat, it turns out to be that I is twice, love is twice, but dog and cat is once. This counting of words in a sentence is done by bag of words. It's very straightforward, but the problem here is it simply ignores the grammar and context. So if I write it opposite, if I write dogs love I, the result will be still the same. It will still count it the same way. So it has no relation with grammar and context. That's the only that's the biggest drawback we have with bag of words. Building on that, we have TF-IDF, which stands for term frequency inverse document frequency. As the name itself makes it clear that the number of times a term is frequent, the number of times that term appears in a document is inversely proportional to the frequency of that whole document. like the most repetitive word, the word which has been there most will have the least weight, and the most distinct one will have the highest weight across the document. Like the common words like the is will get downplayed here, but one of those unique ones like diagnosis in medical text will get boosted. Like these words uh, will have a higher term frequency IDF. The purpose of term frequency IDF is to uh, categorize the common ones to down like to separate the common ones from the distinctive words, so that we have a set of words which is distinctive, which has the maximum meaning in it, which can be used by model further to get a deeper context about the text. So in both these first two steps, we are simply converting text into numerical, as you could see. Then we have one-hot encoding, which creates a sparse binary vector for each word, a long string of zeros with a single one in a unique position. It's like simple. Like if you keep um, if you keep a dog, bark, cat, meow, then bark and dog will be bit closer, and meow and cat will be closer because they have some semantic relationship between them. They have been sparse. They have a vector value which is more close to each other. In multi-dimensional space, the vector value for similar words will be lesser. Like they will be more close to each other. So that's how one-hot encoding works. They can find the semantic relationship between words. They can look for semantically similar words together. So this is the very primary stage of finding semantic relationship between words. If we move into more advanced techniques like embedding, where we have word-to-vec or glob, that takes into dense vectors. The one-hot encoding is sparse vector, but embedding has dense vectors. Like usually it has 100 to 300 dimension, which can capture semantic similarity like very closely. Like it can understand most of the context between the words, like due to its high dimension. I'll tell you an example about this. Like there is a picture also in that slide that if you could see a dot extended towards king, and if you minus man out of it, and you add a woman to that sparse to that vector, the result which comes out is a queen. So how is these machine able to understand that if you minus if you minus man from king and you add woman, then you get a queen as answer. So such kind of vector relationship between the words, between the tokens are done under embedding. It is used to capture semantic similarity at a denser vector, like using denser vectors. Uh, Rather than the approach used by one-hot encoding, which is a sparse vector dimension, where the unique positions are given to words. You can't simply you can't do this subtraction thing in one-hot encoding. You can't do this. But when it comes for embedding, we are able to do this semantic capturing of words. We can capture words more semantically. Then we have contextual embedding using BERT, and GPT, where the meaning of the word depends upon the surrounding, where the context of the token has to be understood before we come up on a conclusion what actually the word is meaning in there. Like again, the same example that bank can be referred to as a financial institution or as a river bank also. So to understand that, we have to read the sentences preceding and succeeding to them, so that what is the meaning of the bank out there in the particular sentence. So such kind of contextual understanding is generated through contextual embedding. where we have examples like BERT and GPT. So there is one more example. Like if you could see, there is encoder and a decoder at the top right of the slide, which shows that she is eating a green apple. Is a sentence fed into the encoder. It converts the sentence into a specific vector. Then the vector is again decoded back to the language which is required. So this whole step itself is covering machine translation. This is actually a transformer architecture where we have an encoder, we have a decoder, takes in the query, converts it into vector, and the vector is that response is also produced in vector. And when the response has to be delivered to the user, we convert back into textual data using decoder. So this was a small demonstration of the working behind the machine translation, the Google Translate or any such machine translation platforms. So if anyone has any doubt till now, I can clear it out in this.
It's fine.
You are good to go.
Understandable.
As we have already discussed before, that if we feed in data which is not balanced, which is imbalanced, one of the aspect of the data set is more, and like there's a there's a chance of majority and minority, then it is pretty much predictable that the model will also come up with a biased output where it will be predicting most of the cases as majority because it has been trained and it has been normalized on such kind of imbalanced data. So balancing matters a lot. We have to balance the data so that we get an unbiased model. The model is not biased towards any particular aspect. Same example, if we feed in 90% positive reviews, the model will start predicting everything as positive, which is useless. So the best practices we can do in such cases are we should not just rely on accuracy. We should also go with precision, which looks for the true positives, and recall, which looks into the actual positives. And the balance between both of them is F1 score, which helps us to understand how well is the model able to learn, how well the model is able to normalize the data set in itself through evaluation metrics. We also have confusion metrics and cross validation used to validate how well the model is able to normalize the data set. According to that, we can use balancing techniques. If we find that the data set is imbalanced, we can do resampling. So resampling has two techniques. Like either you oversample the minority, you create multiple copies of the minority, or you downsample, you undersample the majority, like you lesser the majority. You decrease the majority as majority feature so that the data set gets balanced. Then we have smooth, which is used to synthetically generate minority samples via interpolation. Like it's, um, uh, like rather than you create manually, smooth is a function which can automatically generate the one. It can automatically balance the data set by generating synthetic samples for the minority. The overall purpose of this step is to balance the data set, avoid the model to getting biased, and like extract maximum usefulness from the model. That is the whole purpose of balancing data, so that our NLP models are more reliable. We can rely on them. We can't. There is no scope of doubt on the prediction made by the model. So that could be only possible by applying balanced data set. I believe I made myself clear on this step.
Yes.
Yes. Yeah.
So the very last step before we wind up is build and train the model. So this isn't just the simple one. Like this is actually the main. This is actually the place where the actual game begins. Like the choice of model. Like there is no single best model. Like there is no model which you can term as best. Every model has its own privileges, has its own drawbacks. You have to understand the task and the data before you choose the model. Like depends a lot. It depends heavily on what kind of model you choose for the problem. Like if the model doesn't fit with the problem, then whatever you do, the metrics won't go higher. You won't get a better result out of your model. So picking up the right model for the right task. Like if it's a quick task, like if it's a small sentiment analysis, you can prefer using naive bias. But if you need to have a longer context about that data, like what is going on inside the data. If you want the model to memorize those aspects, then you can bring long short-term memory (LSTM) models. And if the task is really complex, has multiple things to do, has to extract text and fill in forms or create queries, such kind of complicated tasks can be fulfilled using transformers. So we need to match the complexity so that we don't waste our resources, and neither we create too simple, neither we go too simple. So we have to balance out the uh, task, data, and model in a way we get maximum output out of the model. Let's uh, understand the examples. Like in sentiment analysis of review, naive bias is a simple baseline for small data. Like if it's a small data, we can simply use naive bias. Naive bias is actually a probabilistic ML algorithm, uses bias theorem. Bias theorem is a probability theorem used to treat every event individually. So for simple data, it's efficient. But when you come to sarcasm, uh, naive bias won't be able to catch sarcasm from a sequence. You need LSTM. Why? Because for the sarcasm to hit, for the machine to understand the sarcasm, it should have some memory. It should have some context from the past. Okay, what we were talking about. Oh, this was the statement. So according to the preceding statement, the present token might be a sarcastic one or might be a normal conversation. This decision is made by a machine using LSTM and its ability. And not just LSTM, we have more advanced models like GRU, gated recurrent units, and we have there is one more I'm not able to recall right now, but LSTM and GRUs and such RNNs, such memory-based architectures can be used to memorize the context preceding or succeeding the token, based on the use case or task given to you. If Akshay, you might be thinking like if the sarcasm is being handled by LSTM, then what is the use of transformers like BERT or GPT? What are they actually doing? So they have more complex tasks to do. Like a word sick. A word sick has two meanings. It either means cool or ill. A sick could be considered as a slang or as a normal word. So what is the context of sick in a sentence is like more often like LSTM will also fail. Like LSTM is also having a limited amount of memory, limited amount of space to memorize the context, where we need BERT, like transformers, to memorize, to have a context far beyond LSTM could have. So such complicated tasks could be handled by BERT. Then in machine translation, we have RNNs and LSTMs, but these are some old standards. These are old and they are very comparatively slow for long text. But when it comes to transformer, they dominate. They have this parallel processing. Parallel processing. How are they having parallel processing? Through their attention mechanism, through their encoder decoder architecture. That is the reason behind transformers to act parallelly, to process parallelly, so that the impact out of it is reliable, and like it's worthy of what it's giving out. Then we have document classification, like categorizing news. We For such a small task, we can use logistic regression, where we can categorize the different types of news. Like we have news about sports, we have news about science, we have news about religion, atheism, like different news groups, news classifications we have. So logistic regression is pretty efficient in doing this task. And for a fact, I've also created a code block for you people to understand this particular use case. I have made a code where we have applied logistic regression, and we have loaded a data set from News 20, which is a group of multiple news channels, news channels, which has different articles inside the data set. Around 20,000 articles are there of different fields, among which we are able to categorize. Okay, this news articles belongs to sports column, or this news article belongs to this science column. Sir, do we have time to present that code?
Dave, I think we already have exceeded by 30 minutes. So I think maybe, anyways, the concept is pretty overwhelming. So maybe we can stop now. And in the next conversation, we will have a quick recap, so that the code that you are going to walk through and the concept that we have discussed, right, they are able to resonate. But I think we can probably stop now. Uh, that's my suggestion.
I get this. We are already ahead of time.
Yeah. All right. So with that, I think it was a wonderful conversation, Dave. Thank you so much for setting this up. And thank you so much to everyone for extending this conversation. I know that your time is pretty precious. It's Saturday morning, right? And you have got your own commitments to take care of. Thank you so much for extending this. In the next conversation, we will try to make it more enterprising, and we'll bring something which is very, very practical. Thank you so much again, Dave, for doing this. Thank you. Thanks, everyone.
Thank you, team. Thank you,
Thank
team, for
you.
the time.
Thank you, sir.
Thank you, sir.
Focus. Focus.